Hey everyone, I'm Ben.
And I'm Chloe. Welcome.
Today we're going to talk about something that's, well, it's like the hidden language that makes all of science possible.
That's right, we're diving into the world of units of measurement.
Okay, so to get us started, let's chew on this little puzzle. Picture this. You're driving, you see a speed limit sign that says 40 miles per hour, but your speedometer reads 60 kilometers per hour. So the big question is, are you speeding? To figure that out, you have to speak both languages, miles and kilometers. And that's exactly what we're going to help you do today. First, we'll look at why we even need standards. Then, we'll jump into the universal language of science, the SI units. After that, we'll see how you can combine them in cool ways. And finally, we'll unlock the power of conversion so we can solve that puzzle from the beginning. So let's start with the big why. I mean, why can't we all just use our own measurements? Well, imagine trying to build a house if my idea of a foot was different from your idea of a foot. It'd be complete chaos, right? Science absolutely has to have agreement. The standards we use have to be unchanging. Otherwise, everything just gets confusing and ambiguous. Exactly. And that chaos is precisely why scientists all over the world created a solution. It's called the International System of Units, but pretty much everyone just calls it SI. This is the amazing standardized system that means a scientist in Tokyo can look at data from a scientist in Toronto and they're instantly on the same page. No confusion. And believe it or not, this whole huge system is built on just 7 core units. You can see them right here. You've got the meter for length, the kilogram for mass, the second for time, and a few others. Yeah, and what's so wild is how they're defined. It's not like there's a special platinum ruler locked in a vault somewhere anymore. Nope. These are based on universal constants of nature. The meter, for instance, is defined by the speed of light, and the second is defined by the vibrations of a cesium atom. That means they're exactly the same everywhere in the universe. How cool is that? Right. But that brings up a question. Using a meter to measure the distance to the sun or the size of a single atom, that would get pretty awkward with all the zeros, right? So how do scientists actually handle these massive or microscopic scales? And this right here is the brilliant answer: prefixes. These are basically just multipliers that make the base units bigger or smaller. And you already know a bunch of them. Kilo means 1,000. So a kilometer is just 1,000 meters. And centi means 100th, which is why you have 100 centimeters in a meter. It's just a really elegant and simple way to scale things. And here's a little bit of trivia for you. This whole idea, this clean base 10 system, it actually came about during the French Revolution. They were on a mission to standardize, well, everything. If you found that little fact surprising, go ahead and hit that like button for us. Okay, let's keep building on this. So we have those 7 base units, right? Think of them like the alphabet of measurement. Once you have them, you can start combining them to form words. And those words can describe almost any physical thing you can think of. And when we do that, when we combine those base units, we get something called a derived unit. And the name really says it all. It's a new unit that's derived from those fundamental building blocks. This table is a perfect example of how that works. Let's take area. How do you find the area of a square? You multiply its length by its width. So if we measure in meters, the unit becomes meters times meters, which we write as meters squared. Same idea for volume. Length times width times height gives you meters cubed. See, we're just multiplying and dividing those base units. And a great everyday example of a derived unit is speed. Speed is just a measure of distance divided by time. So in SI units, that's meters per second. The unit literally tells you the formula. It's a combination of a length unit and a time unit. Now, speaking of units, there's a really common mix-up we need to clear up: the difference between mass and weight. Mass, which we measure in kilograms, is the amount of stuff you're made of. That number is constant, doesn't matter where you are. Weight, on the other hand, is the force of gravity pulling on your mass. So while your mass is the same on Earth as it is on the moon, you'd weigh way less on the moon because its gravity is so much weaker. It is so easy to get those two mixed up. Be honest, let us know down in the comments if that's one you've stumbled over before. And hey, if you're finding this stuff helpful, this is a perfect time to hit that subscribe button so you don't miss our next explainer. All right, now for what is probably the most practical skill in this whole explainer. Look, we live in a world that uses a mix of measurement systems, so being able to translate between them is super important. We're going to show you exactly how to do that. The secret weapon here is something called a conversion factor. It's basically just a fraction where the top and bottom parts are equal, just in different units. Like we know there are 100 cents in $1, so the fraction 100 cents divided by $1 is actually equal to 1. And the cool thing is, you can multiply anything by 1 and not change its actual value. You're just changing the units you're using to describe it. And we use these conversion factors in a really powerful method called dimensional analysis. Now, don't let the fancy name scare you. It's really just 3 easy steps. Step 1, know what you have, your given unit. Step 2, know what you want to get to. And step 3, the magic step, multiply by a conversion factor that's set up so your old unit cancels out and you're left with the unit you want.
Okay, let's finally solve our speeding puzzle. So step 1, we are given 60 kilometers per hour. Step 2, we want miles per hour. We know that 1 kilometer is equal to about 0.62 miles. So for step 3, we set up our conversion factor with kilometers on the bottom so it'll cancel out, and miles on the top. Then we just multiply 60 by 0.62,
and you get 37.2 miles per hour. So in a 40-mile-per-hour zone, you are totally fine. You are not speeding. See? Once you know the process, it's actually pretty simple. So let's do a quick recap. We saw why standard units are the bedrock of good science. We talked about those 7 fundamental SI base units, and we saw how we can combine them to create derived units for things like area and speed. And finally, we learned how to use conversion factors to translate between different units, like a pro.
And we'll leave you with this to think about. We've talked a lot about science today, but where else in our world are universal standards totally essential for things to just work? You know, think about things like Wi-Fi or USB ports or even the plugs you put into the wall. It's everywhere when you start looking for it.
We really hope this helps clear things up. If you have any questions at all, you know what to do. Drop them in the comments below and we'll do our best to answer. And of course, if you found this helpful, a like, a share with a friend, or subscribing to the channel would mean the world to us. Thanks for tuning in.